This is the normal distribution as an approximation of the binomial distribution. Now, criteria for a binomial probability experiment. It's a probability experiment as a binomial if fallen or true. The experiment is performed in independent times. Each repetition is called a trial. There are two mutually exclusive outcomes, success or failure. Now, success and failure doesn't mean anything good or bad. Success could be something you're studying, like whether somebody failed a test. So you either failed or you passed. Well, success is just whatever you're studying. And then probability of success, P, is the same for each trial. We saw this back in the binomial. Now, for a fixed P, as the number of trials in a binomial experiment increases, the probability distribution of the random variable x becomes more nearly symmetric and bell-shaped. As a rule of thumb, if n times p times 1 minus p is greater than or equal to 10, then the probability distribution will be approximately symmetric and bell-shaped. In other words, you can't do this section unless that's true. And as I say right here, using a normal distribution to approximate it, first verify that n times p times 1 minus p is greater than or equal to 10. That's what we said right here. Calculate your mean. Mu is equal to n times p, and sigma, which is square root of n times p times 1 minus p. And then x is equal to number of successes using x minus 0.5 or x plus 0.5. That's our correction factor because we're approximating a binomial distribution, a discrete distribution with using normal, which is continuous. So we have to have that correction factor. It's always 0.5, so it never changes. Does not 0.2 sometimes, 0.7 other times. Always 0.5. Now here's these formulas again, just to really emphasize it. Mean is n times p. Sigma is equal to square root of n times p times 1 minus p. Now to figure our correction factor, these are the steps we'll do. Determine if your wording includes the number, yes or no question. Draw the graph, adding or subtracting 0.5 such that, case 1, if the wording includes a number, your shading will include a number. Case 2, if your wording doesn't include a number, then your shading won't include it. Let's see what in the world this means. Make up some examples. Probability of more than 35. Well, here's 35. And more than means I shade to the right in terms of our normal distribution. Now, more than doesn't include 35. So I'm going to either add or subtract 0.5 such that it'll match. This doesn't include 35, so I'm going to add 0.5. So we've got 35.5. More than is shaded this way. Now again, if your wording doesn't include 35, then your shading shouldn't include 35. Let's see. Probability at most 10. Well, here's 10. At most means I shade to the left. Now at most 10 means it includes 10. So over here I'm going to add 0.5 and then shade this way. Again, if your wording includes 10, your shading has to include 10. Your whole guideline. See, more than, at most, how about at least? Not that I can spell least, it's bad. At least 70. I'm making these numbers up. We're just trying to see which way to go with correction factor. At least 70 includes 70. So I'm going to subtract 0.5. So we've got 69.5. Again, if your wording includes 70, then your shading has to include 70. Now the one that's kind of an oddball is the exactly case. So let's talk about it. Exactly 20. Now here's 20. Now, obviously, my wording includes 20, so my shading has to include 20. So here we have to subtract 0.5, and we have to add 0.5. Again, if our wording includes 20, our shading has to include 20. And let me do one more example so we see this. See, between 30 and 70. Inclusive. Inclusive means it includes those values. Okay, here's 30. And here's 70. We said it includes those values. So over here, I'm going to subtract 0.5. And over here, I'll add 0.5. And then between, we shade between them. Again, if our wording includes 30 and 70, then our shading has to include 30 and 70. Now that'll be your whole guide. You'll know if you did it wrong if those don't match. Like down here, if I had added 0.5, 30.5, and then shaded, my wording would have included 30, but my shading wouldn't have included 30. So that's what this is talking about, the correction factor. Now by hand instructions. We're going to verify the binomial experiment, or verify it is a binomial experiment, and n times p times 1 minus p is greater than or equal to 10. And then a second thing we'll do is change the x value with the 0.5 correction already figured in to a z-score using this formula. Z is equal to x minus n times p over square root of n times p times 1 minus p. Now, P will usually be given as a percentage. They'll say like 20% of people are watching Friday the 13th today. There's a marathon on AMC. So that would be our P. And then after you get the z-score, look it up in your table based upon shading to the left, right, or in between. Now the TI-83 84 instructions. We'll do our normal CDF, lower bound, upper bound, then our mean, which is n times p, and then our standard deviation, which is the square root of n times p times 1 minus p. We're first going to do these with the calculator, and then I'll go back and do them by hand. Let me save this. What is this? Normal distribution is an approximation of binomial. So, yes, normal distribution as approximation to binomial. Page 01.pdf. There we go. Okay, so let's look at our first problem. It says 80% of students procrastinate on their schoolwork. Well, that's P. When they give you a percent, then that'll be P. So P is equal to 0.8 or 0.80, whatever you want to put. Suppose 200 students are selected. That's N. N is equal to 200. Use the normal as an approximation binomial to approximate probably exactly 150 procrastinate. First we'll do it with the calculator. Well, exactly. 150 means I'm going to subtract 0.5, so this is 149.5, and I'll add 0.5, so this is 150.5. So probability of exactly exactly 150. Okay, so we subtract 0.5, we add 0.5. Now, if our wording includes 150, our shading has to include 150. So for normal CDF, using the calculator, we'll do our lower bound, which is 149.5, and our upper bound, which is 150.5. When I say lower bound and upper bound, I'm talking about what's shaded. See how it's shaded from 149.5 to 150.5? Comma, n times p, so we got 200 times 0.8, comma, square root of 200 times 0.8 times 1 minus 0.8. So this is n times p, and this is the square root of n times p times 1 minus p. Well, let's go put this in our calculator and see what we get. So I'm going to do a second mode, exit out of that. And do second vars to get to the normal CDF, down arrow. And we got 149.5, comma, 150.5, comma, 200 times 0.8, comma, square root of 200 times 0.8 times, and I could put in beginning parentheses 1 minus, I'll go ahead and do that, 1 minus 0.8. Make sure you put parentheses in there. Closing parentheses on that. You don't have to put any closing parentheses at all at the end if you don't want. So anyway, that gives us our answer. 0.0148. Pretty easy if you get the correction factor right. That 0.5. That's kind of the only tricky part when you're using the calculator. Okay, let's look at it by hand. Let's go back to our steps. First, verify we can do it. Now, hopefully these work out. I just made up numbers. But our first step, we take n times p. You should actually do that on the calculator part too, but kind of got sloppy there, I guess. Okay, so we'll take 200 times p, which is 0.8, times 1 minus p, and we're wondering if it's greater than 10. So let's go put that in. I made most of my n's pretty big, so I wouldn't have to worry about that. 0.8 times 1 minus 0.8 is 0.2. And we get 32. Which is greater than 10, so yes, that's okay. Second step is change your x values with a 0.5 correction to a z-score. Well, our x values is up there. So we got x is equal to 149.5, and we get x is equal to 150.5. Keep in mind, n is 200, and p is equal to 0.80. So we could use that formula. Z is equal to x minus n times p over the square root of n times p times 1 minus p. So x is let's see, 149.5 minus n times 0.8, n times p, over the square root of n times p times 1 minus p. And I have to do the same thing with this one. So x minus np over square root of n times p times 1 minus p. So we get 150.5 minus 200 times 0.8 over the square root of 200 times 0.8 times 1 minus 0.8. Now, since we're going to be looking these up in our tables, and our tables are restricted to 2 decimal places, once I plug them in, that's all I'm going to worry about is 2 decimal places. Now, in terms of entering these into your calculator, you had to put parentheses on the top. So I got 149.5 minus 200 times 0.8, closing parentheses on the top, divided by, and I don't need parentheses around the bottom because that's enclosed in a square root. So we got square root, second x squared. I think, did I push that? Yeah, it says second x squared. Oh, there's a square root. Blind as a bat. Okay, 200 times 0.8 times 0.2. 1 minus 0.8 is 0.2. Enter. And this will be negative 1.86. Again, I'll take it 2 decimal places. Now the other one. If I do second enter, that'll bring up the previous entry. We'll save some time. And I'll come up here and change the 149.5 to 150.5. And enter. And we get negative 1.68. Negative 1.68. Now let me check everything there. Minus 200 times, okay. Square root, yeah, that looks good. Okay, so now what we've changed it to is our picture's changed slightly. Used to look like this, and this was in terms of x values. So now this is in terms of y values, or z values. So this will be negative 1.86, and this will be negative 1.68. And we're still finding what's in between. Now our tables in the back are based upon the area to the left. So the between case, if you remember this from a previous section, you start with this, negative 1.68. You're going to look that up in your table. And then you're going to subtract the other one, looked up in your table. Because again, here's negative 1.86. If I take a look at this picture right here, if I erase this area right over here, that'll give me the area in the middle. Now again, I'm going to erase this. I don't want you to get confused with that, but that's why it works. So let's go look this up in our table. Negative 1.68. Okay. Oops. Now 0.8, the hundreds place is right here. So I want this column. Negative 1.6. Here's negative 1.6. I come over to here. Assuming my eyes don't get off, and I get 0.0465. So 0.0465 minus, and then we'll look up the negative 1.86. Well, the 6 in the hundreds place, so we're looking in this column. Negative 1.8. Right here, negative 1.86, we get 0.0314. So 0.0314. And if I subtract those, I'm not very good at decimals, so let me go to my calculator. 0.0465 minus 0.0314. And we get 0.051. 0.0151, yeah. And that's our answer, by hand. Let's compare that against what we came up with up here. 0.0148. Notice it isn't exact. They won't be. So don't get real upset about that. You know, I don't know of any way that you could get it more precise. But the calculators actually will give you a more precise answer because it's not limited by tables. Anytime you're using the tables in the back, you're always just going to be limited by rounding and so forth. Like right here, this wasn't really negative 1.86, and this wasn't negative 1.68. We rounded it to that. So don't get upset if your answers are a little bit off. Now, they shouldn't be a whole lot off. See, this is 0.0003 off. So it's not too much off. Let me save that. There we go. Now let's look at our second example. Here it is. I went to a website, I don't even remember what it's called, Statistics Brain or something like that, and had a bunch of percentages out there, statistics-wise. I don't know if they're valid or not, but it was kind of fun to go and pull information off of them. And this is what they estimate, based upon, they gave a website actually. They said 1.11% of citizens cheat on their taxes. Then suppose 450 citizens are selected, use the Normal's approximation binomial to blah blah blah. Okay, so whenever they're giving you percents, that's your P. So P will be 0.0111, and 450 citizens, so that's your N. Approximate probably at least 10. So at least 10 cheat on their taxes. Okay, so we're going to do it via the calculator first. Here's 10. At least 10. That includes 10. And it's shaded to the right. So I'm going to need to subtract 0.5. And I'm going like that. So again, if the wording includes 10, the shading has to include 10. So we're going to do Normalcdf, our lower bound, which is 9.5. Now it's shaded forever this way, so that's E99. That's how we represent positive infinity. And then N times P, so we got 450 times 0.011, well 3 ones. It sounds like I'm saying it wrong every time I say that. And then over here I'll have 450 times 0.0111 times 1 minus 0.0111. And again, this is the square root of N times P times 1 minus P. Let's see what this gives us. So I'll do second vars, do Normalcdf, number 2. We've got 9.5. I'm not sure why that 6 won't shut off. Let me hit the 6 a few times. There. That was bothering me. Second vars, choose Normalcdf, 9.5, comma, E99. You do the E by doing second comma, and then 99, comma, 450 times 0.0111, comma, square roots, so second x squared, 450 times 0.0111 times, beginning parentheses, 1 minus 0.0111. Enter. And we get 0.02, and I'll take it to 4 decimal places, 0213. Now I realize the answer we came up with here isn't bound by rounding of tables, where we have to have z-scores to 2 decimal places. So, well, now by hand. Now I'm not going to verify. Well, maybe I ought to. We should verify it on that too, but oh well. Once is enough. 1 n times p times 1 minus p is going to be greater than or equal to 10. That's what we need to verify. So n, which is 450, times p, which is 0.0111, times 1 minus 0.0111. Sounds wrong every time I say that. 450 times 0.0111 times beginning parentheses 1 minus 0.0111. Ah! 4.94. It's not greater than or equal to 10, is it? That would have been bad. Let's pretend it is. So this is opposite day. We'll pretend it is okay. I'll have to actually go correct that, so when I do it in class, the numbers work out good. I was so good about looking up statistics, seemed halfway valid, but then I didn't actually check that. No, that's very disappointing. So, oh well. We'll pretend it's okay. Now we want to change the x value with the 0.5 correction to a z-score. Remember, our picture looks like this. We got, here's 10, and 9.5 shaded to the right. So this is our x value, and we want to change that to a z-score. So we got x minus n times p over square root of n p times 1 minus p. Watch it give us a z-score. It's not even on our table or something. Okay, so we got 9.5 minus n, which was what was n? 450 times p, which is 0.0111 over the square root of n. So 450 times 0.0111 times 1 minus 0.0111. Now remember, you have to put parentheses on top when you enter that in. So let's go put that in, see what we get. So beginning parentheses 9.5 minus 450 times 0.0111, closing parentheses on top part, divided by, I don't need it around top, bottom, because we've got a square root. So second x squared, 450 times 0.0111 times, beginning parentheses, 1 minus 0.0111. And 2.03 would be our z-score. So our picture now looks like this. We got z is equal to 2.03. Still shaded the same way. Problem with that is our table is based upon the area to the left. Well, I can do 1 minus z is equal to 2.03 shaded to the left. Because 1 is everything. So 1 is the entire thing shaded. If I subtract off the area to the left, that'll leave me the area to the right, which is what I want. So let's go look up 2.03. And wrong way. Now 0.03, the 3 is in our hundredths place. I'm looking in this column, and we're looking for 2.0. So 2.0, the intersection of 2.0 and 0.03 is 0.9788. Not very good with decimals, so let me go subtract those. 1 minus 0.9788. And we get 0.0212. Using tables and doing it by hand. And not too far off that time. And again, I apologize for this part right here. Guess I should have checked them when I made these problems up, but oh well. I think you get the idea, and that's my goal here. In reality, if this was a homework problem, you would say you can't use it, and you'd go and do the binomial distribution. You can still solve the problem, you just can't use these normal as an approximation to it. Now, if we were going back and doing the binomial, then you remember the Binomcdf, Binom-PDF, you'd have to use that if you're doing it on a calculator. Okay, what's wrong with that? Love how my little tablet blows up every now and then. Let's look at our third problem. And again, I went to Statistics Brain, or Brain Statistics, whatever it's called, and pulled this useful information. It says 87% of American households have outdoor grills. So that's P. P is equal to 0.87. It says suppose 310 households are selected. Use the normals and approximation of the binomial. Now I kind of question this. It's like, how do they know I have an outdoor grill? If there's a government database that's keeping track of all that, then we're in big trouble. So I don't know where they get that at. Could be based upon how many households are in the United States and how many people have registered. But then again, I never register anything when I buy it. So I don't know where they get that. Maybe how many they've sold and the anticipated lifespan of an outdoor grill. So they use that to figure out what percentage. Just guessing. Or maybe they just made the numbers up. Either way, it was something I could use. Okay. Now what they're asking for, approximate probably the fewer than 260. So fewer than 260. So I draw a picture here. Fewer than doesn't include 260. So I do 259.5. And fewer than is shading to the left. So again, your wording doesn't include 260. Your shading shouldn't include 260. So now we're going to do Normalcdf. It's shaded clear to the left, so that's negative infinity or negative E99. And then we'll put in 259.5 n times p, so we got 310 times 0.87. And then the square root of 310 times 0.87 times 1 minus 0.87. Let's see what we get here. So do second vars, Normalcdf, negative, and you get E99 again by doing second, comma, 99, comma, 259.5, comma, 310 times 0.87, comma, square root, second x squared, 310 times 0.87, 87%, and if 87% have it, then 13% don't. This one's easy to do in my head. So you could put 1 minus 8.87 if you want there, but and we get 0.0425, rounding it to 4 decimal places. 0.0425. Okay, let's do it by hand now. I hope this one works. Now again, we want to verify that n times p times 1 minus p is greater than or equal to 10. So n was 310 times p, which is 0.87, times 1 minus p. Let's see what that gives us. 310 times 0.87 times 1 minus 0.87. That looks good. That's greater than 10. 35.061. Okay, step 2. Where am I at? Right here. Change the x value with correction to a z-score. Well, With the correction, we're looking for 259.5 shaded to the left, and this is an x value. So we need to change that to a z-score. So we got z is equal to x minus n times p over the square root of n times p times 1 minus p. So we got x, which is 259.5, minus n, which was 310 times 0.87, over the square root of 310 times 0.87 times 1 minus 0.87. Now again, put parentheses on top when you plug in your calculator. So I do beginning parentheses 259.5 minus 310 times 0.87. Don't put any extra parentheses if you can help it. So close parentheses, divided by, then the square root. So do second x squared, 310 times 0.87 times 0.13. 1 minus p is just, they add up to 100%. So, and we get negative 1.72. So our picture now looks like this. Here's negative 1.72 shaded to the left. So step 3, we want to look it up in our table. Our table is actually based upon the area to the left, so that's perfect. So let's go over here, negative 1.72. I don't know which way I need to go. Not that way. Now the 2 here is in the hundreds place, so I'm looking in this column. Negative 1.7, I get 0.0427. Negative 1.7, yeah, 0.0427. Let's see how that compares. 0.0425, fairly close. Again, our calculator is actually more accurate in that regard. Or if you're doing it in Excel, your Excel will be more accurate because it's not limited by the tables. Last problem. It's kind of sad, isn't it? It's kind of like Christmas time. Last present you're opening. Take a look at this one. 40% of men have noticeable hair loss by age 35. That was out there. I bookmarked that site. There's a lot of statistics I can use to create problems with. Okay, so P is equal to 0.40. Wait a minute, how old am I? Do I got noticeable hair loss? Maybe. Have noticeable hair loss by age 35. Suppose 500 men, so N is 500, who are 35 years old are selected. Use the normals and approximation of binomial to approximate probably between 100 and 200 of them are having noticeable hair loss. Now the assumption is here it includes 100 and 200. Okay, so here's 100, and here's 200. 100 to 200 you shade in between. It includes 100 to 200, so I'm going to subtract 0.5 here. So I got 99.5, and I'll add 0.5. So I got 200.5. And we're shading in between. Again, if our wording includes 100 and 200, then our shading has to include 100 and 200. So we'll do normal CDF. Our lower value, which is 99.5, to our upper, which is 200.5. N times P, so we got 500 times 0.4, or 0.40, comma, square root of N times P times 1 minus P. Let's see what that gives us. So second vars normal CDF. 99.5, comma, 200.5, comma, 500 times 0.4, comma, second x squared 500 times 0.4 times 1 minus 0.4, which is 0.6. If the first one's 40%, this has to be 60%. Enter. And 4 decimal places, we get 0.5182. Now let's look at it by hand. Now I will tell you, some people get all excited on these problems. They must love them or something. I don't know. When I give a test, people start subtracting and adding 0.5 all over the place. The only time you do that is where it actually says use a normal as an approximation of the binomial. You don't use it on the other sections. Okay, by hand. Our first step is verify n times p times 1 minus p is greater than or equal to 10. Well, n is 500 times p, which is 0.40, times 1 minus p. Let's see what that gives us. 500 times 0.4 times 0.6. Get 120. Well, that's definitely greater than or equal to 10, so we're okay there. Second step, change your x value with the correction to a z-score. Now in this particular one, we have two x values. So we have x is equal to 99.5, and we have x is equal to 200.5. We'll change them both to a z-score. So this will be, let me write my formula down first. Sorry about that. Z is equal to x minus n times p over the square root of n times p times 1 minus p. And this one same way. X minus np over square root of n times p times 1 minus p. Okay, so we got this z-score is equal to x, which is 99.5, minus n, which was 500, times p, which is 0.4, over square root of n, 500 times 0.4 times 1 minus 0.4. And this one, we'll have 200.5 minus 500 times 0.4 over square root of 500 times 0.4 times 1 minus 0.4. And let's see what these come out to. Again, parentheses are on top when you put them in. So I'll put a beginning parentheses 99.5 minus 500 times 0.4, closing parentheses divided by square root of 500 times 0.4 times 0.6. Ooh, that doesn't look good. Did I type that in right? 99.5 minus 500 times 0.4, close parentheses divided by square root of 500 times 0.4 times 0.6. That won't be in our table. That's what I'm saying. That's no good. I mean, it's okay with technology, but oh well. Maybe that's useful to show you something not on the table anyway, to show you how to handle that situation. Okay, let's plug in the other one. And so I'll do second enter, bring up previous entry. And I'm just going to up arrow and left arrow over to change that. Now, if you need more digits there, you can do a second delete to throw it into insert mode. And then it's 200. 200.5 minus 500 times 0.4, enter. That looks much better there. I just made these numbers up. I probably should have checked them a little bit more. 2 decimal places, 0.05. Okay. Now what a picture looks like. Is now we got negative 9.17. And over here we got 0.05. And we're shading in between. Well, we can't look that up directly. So what we're going to have to do is when the between case is always this way, you're going to look up the area to the left of 0.05, and you'll subtract the area to the left of negative 9.17. Again, if I were to take this and subtract off the area to the left of negative 9.17, that'd give us what we're wanting. Because it has to be always the area to the left for the tables. Well, let's look this up. Negative, or 0.05. That's weird. 0.05. Which means I'm going to look up 0.0 and then the 500ths column. Which way do I need to go? This way. Well, here's 0.0. In the 500ths column, it'll be right here. So I'm going to use 0.5199. Okay, negative 9.17. Well, the 7 is in the hundredths place, so I'm going to look up in the hundredths column, the 0.07. And negative 9, this is the closest. And you notice they're all 0.003. So again, with tables, the best I can do is what's this one here? I guess this is the very smallest one. You see how it's 0.0002. Since it exceeds the limits of my table, I just have to go to the very smallest z-score, which is right here. So minus 0.002, which would give us 0.5197. Oh, I hate decimals. I think that's right. You subtract those. 0.5197, 0.5182. Not as close as before, which isn't surprising, unless I made a math error. Because of some of the problems we just experienced that way. Again, this is the accurate way. Well, if it's accurate, why don't they require you just do it on technology? Why show tables? Why use this and so forth? The only reason I'm showing it and even having it available there is if you go on to use it in another class, sometimes they have you do it by hand. Not because they want to be mean, but a table, I can print this off and give it to you in homework for free. It requires you not to have to buy anything. Now, to do it on the calculator requires you to go out and buy one of those $150 calculators to do it. Now, Excel is a very popular option for other classes because Excel is basically free. Every computer lab and every campus has Excel. I shouldn't state that, but I'd say I'm 99% confident that between 99% and 100% of them have computer labs. But anyway, you see it comes up different. Used to be teaching online statistics was a nightmare. We came to this section especially. Not all sections are like this, but some of them were. And the students' answers wouldn't match when they used technology. So I would have to go in because it counted them wrong because it had the by hand version in there, and it would count them wrong. And I had to go through and correct all of it, putting the points back on there. Well, they've improved that, So they put both types in there. They put if you worked it by hand, that answer, and if you worked it by technology, they put that answer. And I was blah 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 and wasn't paying attention to what I was doing. Did I just save that? I think I did. Shouldn't be mindlessly talking when I should be paying attention. Okay, now I believe we're done. I think that was the last problem. Let me look. Yep, that was the last one. So let me stop the recorders. There we go. And stop this one.